14, I had no idea, because I didn't know what net force was. What's the difference in net force and net force?
Okay, so 15 and 14.
Oh,
13 and 14. All right, so if we read 13, an astronaut on a spacewalk discovers that his jetpack no longer works, leaving him stranded 50 meters from the spacecraft. If the jetpack is removable, explain how the astronaut can still use it to help return to the ship. Okay, so what he can do is he can throw the jetpack. So for every action, there's an equal and opposite reaction. So if he throws the jetpack, so let's say his ship is this way. His ship is behind him. Okay? If he throws the jetpack in the opposite direction from him and the ship, it's going to push him back. Because for every action, there's an equal and opposite reaction. So his action would be throwing the jetpack. The reaction would be him moving backwards as a result of that.
So is he just moving because he's in space and he doesn't have ground, like holding him down?
Oh, yeah.
Okay. I'm sorry,
Yeah.
I guess I was just like, how
Yeah.
does that work? 'Cause I was imagining, I guess.
Yeah, there's no gravity. So that normally, I guess you might think of our action and reaction as being gravity and us keeping us on the ground. But there you don't have that. So if he applies a force in one direction, that means he's going in the opposite direction. And really, that's even true. Well, really, that's even true here. And if you think about how a rocket takes off in the first place, okay, so you have very large controlled explosion that's pushing straight down, so the rocket goes the opposite direction, straight up. So there's an action downward. There's an equal and opposite reaction of the rocket going up. And the force with which that downward is what's going to give the rocket the speed to eventually escape the Earth's atmosphere. Okay, so that was 13, and you said 14 was the next one? Or 15? 14.
14. I tried to figure out what net force was.
Net. Net is just what's left over after you've taken everything else out of consideration. So like your net pay is what's left over after taxes and health insurance and all that kind of stuff. Same thing here. Your net force is the force that actually goes to moving that particular object, whatever it is. When we take out the force of friction or the force of gravity or any other forces acting on it, the force that actually causes it to move. So is it possible for an object to move in one direction that is different from the direction of the net force acting on the object? Yes. So if we have an object, let's see if I can write on this, draw a little diagram, if I can. All right, so I'm going to go back here. I know I can draw right here. So let's say we have an object that's going to go, that has a force applied, a net force applied to it in this direction. But the object itself goes off in that direction, maybe. They're asking, is that possible? And why would that be possible? Okay, well, if the net force, remember, is mass times acceleration. Acceleration is a vector. Remember? Okay, so acceleration could be acting in that direction because it's a vector. But the object's speed or its velocity could act in another direction. And so that's why the object would go in a different direction than the force that's actually applied on it. Because acceleration is a vector. And remember, acceleration is change in velocity over change in time. So if that, and that's a vector, so if that velocity vector has a different direction than the acceleration vector, then yeah, it's going to go in a different direction. That's all it was asking. Okay.
So when it asked for like the forces, like I think there was one that asked for 3 forces or something. That's so the gravity, friction, like is that what was?
Well, it depends on the situation. Depends on, so which one were we
Oh,
referring to?
well, like 7, it asked for the forces, but I was like, yeah. Wait, no, maybe it didn't. What is my answer?
Okay, so 7 says, as you hold the book at rest in your hands, 2 forces are being exerted on the book. Are those forces equal and opposite in magnitude and opposite direction? Are these reaction pairs? Okay, so I'm holding this book in my hands. What forces are acting here? No, because not necessarily. What's holding this book up? My hands.
It's yeah, but I thought it had to be some science word.
Bicep muscle. What is that bicep muscle? A force is a push or a pull. That's all it is.
I didn't know that.
So what is my bicep doing when it's holding this thing up? It's pushing up on the book, right? Okay. Pushing up on the book. And I'm doing that with my bicep muscle. Okay. What else is happening? The book is also pushing down on my hands. Okay. Are those equal and opposite? Yes, because otherwise there would be the book. Sorry, I woke you up, didn't I? Now you gotta ask. So does that part make sense?
Okay, so anything can be a force. It doesn't have to be some science.
It's a push or a pull.
Okay, well I didn't know that. Cool.
I am applying force to this wall right here, right now. Am I actually doing anything? We'll get into this in the next chapter. Am I actually doing anything? No, because the wall is also pushing back on me, and the wall's pushing back on me more than I'm pushing on it. Okay, so nothing's getting done, but it's still a force. A force is a push or a pull. I pulled it. That's a force. I applied a force to it. That's all it is. Now, the question then becomes, is it an action-reaction pair? Is that an action-reaction pair? The correct answer on that would be no, but why not? Every action force has a reaction, but every force that's applied is not necessarily an action-reaction force.
Because they're not all equal like you in the wall.
Because they're not all acting on the same object. An action-reaction pair has to act on the same object. Okay?
Aren't they both acting on the book though? Gravity and your hands.
Okay, what is gravity acting? Not necessarily. Gravity is acting. Okay. There is a force of my hands on the book. Okay. There's a force of gravity. There's also a force of the book on me as well. So they're not action-reaction pairs. Let's see if I can get a better explanation of that. The forces are not action-reaction pairs because. Oh, I said that backwards. I'm sorry. That's why it didn't make sense. They're not action-reaction pairs because action-reaction pairs don't act on the same object. So change that in your note. Action-reaction pairs do not act on the same object. So we were talking about the rocket. Okay. The rocket, there's a force acting down. Okay. The force of that explosion pushes downward. Then there's another force that acts upward that causes the rocket to go off in space. Those are action-reaction pairs. They're not acting on the same thing. Okay? They're acting on 2 different objects. Okay? So action-reaction pairs act on two different objects. What our situation was doing was acting on the same object.
So, like, question. Going back to the example in our little house, like the bike to the ground, like the bike to the ground, and the ground to the bike.
I see what you're saying, and I want to make sure I tell you right. So just give me that 1 second, because that was a.
I'm sorry, I just know that.
No, I know, I understand. No, those are good questions. I'm just trying to find the example because I want to tell you the right thing. Oh, that wasn't in this PowerPoint. It was in the Nearpod, wasn't it?
Yeah.
Okay. If the two things are acting on different objects, they would be considered an action reaction pair. Your book talks about in terms of a car. So a car's tires are applying a force to the road, and all right, action reaction. One part of the Newton's third law, action reaction pairs are always on different objects. As a result, the two forces do not cancel out. Car accelerating from rest. As the car's engine turns the wheels, the tires exert a force on the road. So you start the engine, that engine causes the tires to exert a force on the road. And this would be the same for the bike example. It's just in the bike example, you're the engine, right? Okay. By the third law, the road exerts an equal and opposite force on the car's tires. It is this second force which acts on the car through its tires that propels the car forward. The force exerted by the tires on the road does not accelerate the car. Okay, so the tires are applying a force to the road. Okay, but then the road is applying a force to the tires. And it's that second force that causes your car to go forward. Okay? Think about it. On an icy road, it's very difficult for you to move forward or move in the direction you want. Why? The road is not really applying a whole lot of force to your tires, so they just keep spinning, right? And they're not moving you forward necessarily. Okay? Or the same thing if you go driving on the grass and you get in a mud puddle, and those tires just keep spinning and spinning and spinning, because there's not enough force applied on those tires to move it forward. And so you just keep sitting there, not going anywhere. Okay? Since the paired action-reaction forces act on different objects, they generally produce different accelerations. So the force that the tires apply on the road has a different acceleration than what the road applies on the tires. Hence, you move forward. Okay? Hopefully. That's the idea. Okay? So does that make sense? Okay. So they are not acting on the same object. So they are action-reaction pairs. The tires are acting on the road, and the road is acting on the tires. They're not acting on the same object. But they're not acting on the same object. The tires are acting on the road, which is not the same object. It's not a tire, it's the road. The road is acting on the tires. It's not the same object. It's not the road, it's the tire. So since they're not acting on the same object, then that's an action-reaction pair.
Okay, even though they are the same set of pairs, they're just working on different things.
Exactly.
Yeah.
Yeah. Great.
I guess these little, examples, object on person on object. But I guess the different sounds. Okay, so I'm just gonna.
Yeah.
But I think.
Yeah, you're overthinking that they're not acting on the same thing. So the two forces are not both pushing on the table. Okay, that would be acting on the same object. They're acting on two different objects. Craig, did you have a question? Number 8, yes.
I thought you had to keep that thing like right above it, and I didn't know it was
All right. Number 8. All right, so number 8, I think the main thing is going to be to look at the fact that they are, force 1 and force 2 are equal to each other. So a 70-kilogram parent and a 19-kilogram child meet at the center of an ice rink. They place their hands together and push. The acceleration of the child has a magnitude of 2.6 meters per second squared. What is the magnitude of the parent's acceleration? So yeah, you're just going to set the two forces equal to each other. And so the mass of the parent times the parent's acceleration, which we don't know, has to equal the mass of the child times the child's acceleration. Because they're starting at rest, and they're putting their hands together and they're pushing. No, it is not. The last chapter was mass times velocity, and that gives us momentum. This is mass times acceleration, which gives us force. Okay? They're pushing against each other. So obviously, the force of the parent, since he weighs more, is going to be different than the force that applied by the child. Okay? Child's going to go flying backwards a whole lot faster than the parent will. Okay? So, and that should make logical sense to you. If you look at the math in it, the parent's acceleration comes out to be 6.69 meters per second squared. That's a whole lot slower than that child, which makes logical sense, right? Let's see if I can blow that up a little more. Again, I did not do, if you look at your answers in the back of the book, they are all in correct significant figures. I just worked it out and moved on. Okay, anything else? Mm-hmm. Okay. So, for number 1, the answer is no. It is not possible for a stationary object to have one force acting on it. If it did, it would not be stationary anymore. It would be moving. So it can't have just one force. Number 2, A is 0.821 meters per second squared. B is 2.57 meters. 0.821.
Can you tell me which formula you get for part B?
Let me give you all the answers and then I'll come back. Okay. That way we'll get them all done. Number 3 is 481 kilograms. Number 4 is 5,700 newtons. Number 5 is 41 kilograms. Number 6 is decrease and 0.0018 meters per second squared. Number 7A is force of gravity. Force your hands exert on the book. And B is yes. And C is no. Action-reaction pairs act on different objects. 6 is 0.7 meters per second squared. Number 9, a non-zero net force. Number 10, acceleration triples. Number 11, I'm going to say the answers can vary because they're asking you to come up with an example. So the example they give, and you don't have to necessarily write all this down. Okay, so the main thing is, so you push on a crate and the crate doesn't move. Like I was pushing on the wall. The wall's not going to move. Okay. The action force is you pushing on the crate or the wall. The reaction force is the wall pushing back on you. That's just an example of action reaction. Number 12A, the shopping cart remains at rest because there's no net force acting on it. B, pushing on the cart exerts a net force, and so it moves. And C, the acceleration is force divided by mass. Because Newton's second law is F equals ma. F is your force, it's your push. So if I push on it with a certain force, the acceleration is going to be equal to that force divided by its mass. Think about that in everyday life, and that'll make sense. If I have an empty shopping cart, I can push that thing, and it'll be going pretty fast through that parking lot because it's empty. But let's say I fill it up with groceries, or I fill it up with toys, or fill it up with people, or whatever. When I try to push it, it's going to be a lot harder because its mass is increased. So I'm going to push harder, that's more force. My acceleration is going to be slower. Okay? 14. Astronauts should push on the jetpack away. Should push the jetpack away in the direction opposite from the spaceship. So it opposite from the spaceship. 14. Yes, it is possible. The net force on the thrown football is due to gravity alone. Its acceleration is always downward, but the ball moves not downward, it moves. I think it's giving you an example of how you can have a force, an acceleration applied in one direction and the ball going in another. 15A, F1 is the force exerted on the car. F2 is the force exerted by the ground on the car. B, they're equal and opposite. So F2 equals negative F1. 16 is 1.8 newtons. 17 is negative 1.23 meters per second squared. 18, we already did that one, but A is 1, again, they're doing significant figures. A is 1,000 newtons, B is negative 1,000 newtons, and C is 2,600 newtons. Okay. Any questions? Say which one?
Number 2.
Acceleration triples. Force triples, acceleration triples. Mass is not going to change. Okay, so those are kind of easy questions because mass is constant. It doesn't matter unless you, mass is constant. So if you change the force, the acceleration is also going to change by the same amount. Yes, ma'am.
Why is number 8 not negative?
You could make it negative if you want to. The negative sign just means that it's going in the opposite direction.
Okay.
I wouldn't have counted it wrong.
Okay, so like number 17, it says that one is negative.
Right, because they're going in opposite directions.
Okay.
Because it's pushing away. So if you put the negative, don't count it wrong. It's fine.
But if you don't put the negative, then maybe it's randomly.
It's a good question. Let's see. I would say probably yes. So be on the safe side. Put the sign.
So how did they get negative 117?
So airplane lands, begins to slow down as it moves along the runway. Its mass is going to break. Okay, the net braking force, that 4.3 times 10 to the 5th, that's a negative number because it's braking. Well, you're putting on the brakes, right? So you're slowing down. So it's acting, the brakes are acting in the direction opposite than what the plane is moving, hence slowing the plane down. So the 4.3 is what I would put as negative. Mass can't be negative, right? That's impossible. So, anything else?
So on B, can I just see if I can use this one more?
The on what? 2B?
I used delta x VIP plus half x squared.
You are correct. Yeah, that's what you would do. So you would use F equals ma to find the acceleration, and then you would plug it into delta x equals VIT plus 1/2 AT squared.
So theoretically, you okay. That just seems counterintuitive. Okay, cool. Never mind. I must have rounded it because I got 2.05. So that was just.
Or put in a decimal somewhere. Somewhere, yeah. The initial velocity is 0 because they're starting from rest, so that whole term falls out. And it just depends on your acceleration and your time. That's probably it.
Why can you not use the formula that's just acceleration equals change in velocity over change in time?
Because we're looking for distance. We're looking for how far it went.
Okay.
We're not looking for its speed. We're looking for how far it went.
Okay.
Yeah. Okay. Anything else? Let's talk about 5.2, or start talking about 5.2. We won't necessarily finish it today, but we'll start it. So let's go presentation mode. So in 5.2, we're looking at applying these Newton's 3 laws. And so we've talked about Newton's laws already. Here we go. And one of the main things with applying Newton's 3 laws is we're going to be drawing, and you've already done this when we did velocity, but you're going to do it some more here. And we have a name for it. We are going to be using what's called a free body diagram. Okay, so free body diagrams, it's just where we lay out the vectors. Okay, we lay out what direction they're going in, and we get their components and all that kind of stuff. So a free body diagram is just a drawing that shows us all the forces acting on an object. And that's going to be important because sometimes we have forces like gravity that we have to consider. And in the next section, we're going to be talking about a force called normal force. And then we have a force due to weight. So there are a lot of forces acting on something, and we need to draw all those vectors out. Okay, so to simplify, I think that's what it's supposed to be, a real life situation in a free body diagram, the object is often represented as a point. So we're looking at this particular example. We have the astronauts working on this particular object right here. So that's our point. Object, or the astronaut at the bottom is pushing up on that object. Okay. The astronaut on the side is pushing to the side. So we have F1 and F2 for astronaut 2 and astronaut 1. Those we are going to break up into our X and Y components because one is going in the X direction, one is going in the Y direction. Okay. So we're going to use that to solve these Newton's laws problems. Once all the forces are drawn and we get our X and Y coordinate system, we can then resolve that. That means we divide it up into its components, its X components and its Y components, just like we did with velocity. No different. Okay. When we know those X and Y components, then we can plug that into Newton's second law. Okay, so here's an example. All right, so back to that example, we got the astronaut pushing on whatever this is. It's an object, doesn't matter. We have one astronaut that's pushing up. We have one astronaut that's pushing to the side. So each force has an x and y component because it's a vector, okay? So force number 1 has a x component, which is the force with which he pushes up on the satellite. So he's pushing up, and the problem tells us with 46 newtons of force. So his x, F1x, this one right here, is 46 newtons because he's pushing on the side of it. So if this is a satellite, he's pushing this way, 46 newtons. He's just pushing this way. So it does not have a y component. F1 does not have a y component because he's not pushing up, pushing straight. Astronaut number 2 down here, he's not pushing horizontally, he's only pushing up. So he has no x component, but he does have a y component of 46 newtons. They just happen to be the same. There's no significance in that. Okay. Next, we find the acceleration in the x and y direction using the x and y components from Newton's second law. Okay, so we're going to add up all of the x components for the forces and all of the y components for the forces. So the x components would be F1 x component plus F2 x component. 46 plus, remember, F2 is 0 because he's pushing up, not out. Okay, so that's 0. And then we just plug and chug and we can find the acceleration in the x direction. Okay. Same thing with Fy. Okay, the forces going up are going to be equal to the 2 astronauts' forces pushing up. The first astronaut does not push up, so he has a 0 force up. The second astronaut pushes up with 46 newtons. So I can rearrange and find AY. So are we all good up to this point right here? Okay. So what we're going to do now in this section is we've just rearranged those equations to solve for AX and AY. We know how to do that right because we know the mass. So we're just going to plug in. We're going to solve for AY and AX. That's what they do right there. 46 divided by 940. That's the acceleration in the x direction. Acceleration in the y direction is 46 divided by 940. Remember, they just happen to be the same. Y is the seconds squared. A Newton is a kilogram meter per second squared. So wherever you see that Newton, it means kilogram meter per second squared. So if we divide that by a kilogram, we end up with meters per second squared. It's in there.
That's probably important.
Yeah. Not for this test coming up. Not for the test we just did. This test, we just started this chapter. So, all right. So now to find the acceleration. Now, this just told us acceleration in the x direction, acceleration in the y direction. We need the actual acceleration. So we got to pay attention to this part because this is where we go back to what we did, similar to what we did in the velocity. All right. So this is acceleration in x direction. This is acceleration in y direction. So the actual acceleration is the resultant of those two vectors. It's combining those two vectors together. How do we do that? Pythagorean theorem. So A is equal to A squared, A in the x direction squared, plus A in the y direction squared, and then we take the square root of it. So to find the actual acceleration, we're going to square them, add them together, take the square root. Okay. To find the angle of that force or that acceleration, we're going to do second function tangent, just like we did back in Unit 2 with velocity. Okay. So remember, we'll have an AX going in the x direction. We'll have an AY going in the y direction. The resultant or the combination of those two vectors is our acceleration. Unit 2. Yes, the whole unit was. But instead of doing acceleration, we did velocity. Okay. Okay, you ready? Does that good there? Okay. All right, so here's an example. So suppose the force exerted by astronaut 1 in figure 5.7 is increased to 58 newtons. So again, they don't have to be the same force. If everything else in the system remains the same, what are the magnitude and direction of the satellite's acceleration? Remember, magnitude just means the number. Direction would be the angle, okay? So we're going to do the same thing. We're going to find the component of the x acceleration, component of the y acceleration, use Pythagorean theorem to find the acceleration, use inverse tangent to find the angle. So if we go back, all we're going to do different. So wait a minute. Who is heavier? Astronaut 1. Okay, so astronaut 1, instead of being 46 newtons, he's 58. Okay, so that means down here, this is going to be 58. Everything else there will stay the same. So this guy is going to be 58, which means that will change. So that means this will change, this will change, this will change, and that will change. Okay? So all they're doing is going back through and changing those numbers. So when you take 58 and divide by 940, that's where they get the 0.617 from. 0.0617. Meters per second squared. So that means this is going to be 0.0617. .079, and then that's going to change down here. Second function tan, and we get like 32. Now, the other problem said 38 is probably because I am severely rounding all of these numbers, and probably I shouldn't have done that. But so that's where those changes come in, okay? Several types of forces that we encounter in everyday situations. They are normal forces, forces exerted by gravity, and forces due to stretch or compression. We're going to talk about the first two very briefly. Okay, so normal force. When an object sits on a surface, it's subject to two forces. We have the downward force of gravity, and then we have the upward force of the table. Okay, so downward force of gravity is what we call weight. Mark that down, okay? Weight and mass are not the same thing. So in this book, they refer to weight as a W, and it's equal to mass times gravity. Sometimes you may also see it as F subscript W. That's force due to weight, and it's mass times gravity, okay? And it's always acting downward, always. Straight down. Okay? Always acts straight down. That's the object's weight. Well, to counter that and to balance that, we always have an upward force that we call the normal force. And it's always acting straight up. Okay? Otherwise, your bowl of soup wouldn't sit on the table. It would be on the floor, right? Because the table doesn't push up on the bowl of soup. Guess what's happening to the bowl of soup? Falling, right? So your force due to weight is acting down. There's also a normal force acting up. Okay? Right here. My book is pushing on the table because of its weight. The table is pushing back on the book. That's a normal force. And they both act in opposite directions. One is straight down, perpendicular. One is straight up, perpendicular. Okay? And that's what we call the normal force. So they put in, or sometimes you may see it FN. That just means normal force. And know that it always acts perpendicular, straight up. Okay? All right, 90 degrees. That's what we mean by perpendicular. Okay. In general, the force exerted perpendicular to the surface of contact between the two objects is what we call the normal force. Okay, so make sure you know that it acts perpendicular to the surface. That's going to be really important in the next chapter when we start incorporating friction and when everything is not on a nice level surface. Okay, so normal force acts perpendicular to the surface. Weight is straight down.
Really quick, I just saw the diagram that, like, okay, so normal, like the bolus is down, down, pressing up. Is that what we just said?
The normal force is pushing up. Normal means the force perpendicular to the surface.
Is that the table?
The table is the surface. So the force acting perpendicular to the surface. Okay. Our surfaces are not always going to be flat, though. Sometimes our surfaces are going to be in an incline. So our normal force will be perpendicular to that incline. The weight of an object is equal to the force acting on it, that force of gravity acting on it. So weight is always represented as force times gravity. Okay, and that's just applying Newton's second law in the situation of gravity. Okay, so the weight of an object is equal to its mass times its acceleration due to gravity. Weight is always in newtons. So please be careful when you say the word weight. When weight is in the problem, we are talking about force due to gravity. It is not grams or kilograms. Write that down somewhere. Weight is not grams or kilograms. It is newtons. Or if we were in English units, it would be pounds. And what do you weigh yourself in? Pounds. Okay. So, anyway. So weight and mass are not the same thing because they change. Weight changes due to gravity. Mass never changes. Mark that down somewhere too. Mass never changes. Weight changes depending on where you are. If I'm at a place with lower gravity, I don't weigh as much. If I am at a place with higher gravity, force of gravity, I will weigh more. That's why I don't want to go to Saturn. Because I'll weigh a whole lot more than him. This is true. So, weights, we're just talking about weight in general. We're not talking about muscle mass. So my muscle mass would probably be great. All right. Anyway, applying weight. So weight can change in accelerating systems. And this is just like a concept type thing. So when you get in an elevator and you just kind of feel a little heavier. Okay. The sensation of having a different weight due to your accelerating environment, such as moving in an elevator. That's referring to your apparent weight. You don't actually gain mass. You're just moving at a different speed, and so your force is a little bit different. Okay? In the opposite direction, so somebody who's training to be an astronaut, you have to get used to the experiencing weightlessness. Okay? where you basically don't have any weight. That's why you're floating. And that's the same concept, but you're going in a different direction. All right. Make sure you check Schoology for tonight's homework. Pay attention to the numbers because I didn't necessarily go in order this time. So make sure you pay attention to the numbers. It means you might be ahead. So, all right. Y'all are dismissed. NHS, like I said, if y'all have time to help me, if you want to go to your study hall, check in with your teacher and all that good stuff, and then come back and we'll start getting started.
Tuesday or Thursday? That's all right, because I might not be able to make it. Well, I'm just on it.